the overall of Iptables and firewall. Iptables is a firewall tool built into the Linux system. It helps protecting a computer by controlling network traffic. An administrator can set rules to allow or block traffic based on the protocol, IP address, and port numbers. Because it is flexible and open source, Iptables is widely used to secure Linux system, while a firewall is an important security tool that monitor and controls network traffic using set rules. It acts as an protective barrier between a trusted internal network and untrusted external network. The importance of network security is that it is important because it keeps data, system, and users safe from online attacks. It stops unauthorized access, data stealing, and system damage. Good network security also ensure a safe communication, protect privacy, and keep system running without problems. The goals are to understand how Iptables works as a host-based firewall in Linux, to configure firewall rules that block insecure network services, to analyze how firewall actions such as drop and reject behave, to verify firewall performance using basic network and security testing tools, and to evaluate firewall effectiveness and suggest secure, innovative, and cost-effective solutions for real-world use.
Now I will explain about implementation environment. So our testing platform is Kali Linux, distribution specifically engineered for security assessment and penetration testing. This provides us with a robust pre-configured environment ideal for our work with firewalls. A critical first step was verifying the tool at the core of our project, Iptables. As you can see the first terminal screenshot, we run the command iptables -- version. The output confirms we are using version 1.8.8, which utilizes the modern NF-tables framework. This check ensured our system had a fully operational and up-to-date firewall utility. Next, we need to view the default firewall state. Using the command sudo iptables -l-n-v with elevated privilege, we list all active rules. The output displayed here shows the 3 default chains: input, forward, and output, each with a policy of accept and 0 packets processed. This blank state was crucial. It confirmed that no pre-existing rules will interfere with our test, providing a clean and controlled starting point for our configuration. This environment verification was foundational to ensuring the accuracy and validity of subsequent results. So now the configuration and verification of our firewall rules. Our goal was to block common but insecure services. We executed 3 specific iptables commands to achieve this. First, to block standard web traffic, we use sudo iptable -a input -p tcp -dport 80-j drop. This appends a rule to the input chain to silently drop all TCP packets destined for port 80, which is HTTP. Second, to block file transfer protocol, we use sudo iptables -a input -p tcp -dport 21-j reject. This rule rejects FTP connections on port 21, but unlike drop, it sends an explicit connection refuse message back to the client. Third, to block the unencrypted telnet service, we use sudo iptables -a input -p tcp -dport 23-j drop, again applying a silent drop. The key to system administration is verification. After entering these commands, we immediately ran the list command again, sudo iptables -l-n-v. The output shown in the lower screenshot is our proof of successful configuration. We can clearly see our 3 new rules at the top of the input chain. Port 80 is set to drop, port 21 is set to reject with a specific ICMP message, and port 23 is set to drop. All packet and byte counters are at 0. Waiting for traffic to hit them, this visual confirmation was essential before we begin any testing. So on this page, we shift from configuration to active testing using common network client tools to attempt connections through our new firewall. The first test targeted our HTTP block. we use the curl command to try to access http://localhost. Curl is a tool for transferring data with URLs. When this command is executed against a locally running web server, it should fetch the home page. However, under our configuration, the connection simply hangs and eventually times out. This is classic behavior of a drop rule. The packets vanish into a void and the client receives no response, demonstrating stealthy silent blocking. Next, we test the FTP rule. Using the FTP localhost command, the system first attempted an IPv6 connection to port 21. The immediate error was connection refused. This is the direct result of our reject rule in the action, providing clear feedback. The client then fell back to IPv4, resulting in the bad file descriptor error, which is another form of connection failure. This sequence perfectly illustrates the difference in user experience. Reject gives an immediate, explicit denial, whereas drop leaves the client waiting. This initial client test provide real-world evidence that our rules were not just entries in the table, but were actively and correctly intercepting and handling network traffic as designed. So for this page, it completes our testing phase with telnet and introduce a external scanner's perspective. We begin with a direct telnet test using telnet localhost 23. Similar to the initial FTP test, the client tried both IPv6 and IPv4 addresses. The result was an immediate connection refuse message. This is interesting because we configured a drop rule for port 23, which should cause a timeout. This connection refuse actually indicates that there is no telnet service listening on this port at all on our Kali machine. The firewall's drop rules is present, but it's secondary to the fact that the service isn't running to accept a connection in the first place. This highlights an important layer of security, not running necessary service. To get the true external assessment of our firewall's footprint, we employ Nmap, the industry standard port scanner. Running Nmap localhost provide a definitive report. The scan results are clear. Port 21 for FTP, 23 for telnet, and 80 for HTTP are all reported with a state of filtered. This filtered state is exactly what we aim for. It tells a potential attacker that a firewall or filter is actively blocking the probe, obscuring whether a service is actually running or not. The Nmap results objectively confirm that our Iptables rules are effective from a security perspective, successfully masking the true state of these ports on our system. So for this page, firewall rules configured in a live session are typically lost on a reboot. For a real-world security solution, this is unacceptable. To solve this, we install the Iptables persistent package as shown in the detailed terminal output. We run sudo apt install Iptables persistent. This package also brings in its dependency netfilter persistent. The installation process captured here is straightforward. Once installed, this package automatically saves the current Iptables rules to a file and reloads them during the system's boot process. The note at the bottom of the page serves as our final summary and confirmation. It states that the installation was successful and reiterates the core findings. All targeted ports were shown as filtered during the Nmap scan. Furthermore, our client-side test using curl, HTTP, and telnet clearly demonstrated the distinct behavioral differences between the drop action, which results in silent timeouts, and the reject action, which provides an immediate explicit connection refuse message. This step moves our configuration from a temporary lab experiment to a durable security posture, ensuring that the protective measures we have tested and verified remain in place indefinitely, which is the ultimate goal of any security implementation.
So now I will explain how we validate that our Iptable rules really block the target service and what the result mean. First, we perform all tests in a controlled environment, local environment, using the loopback address as you can see 127.0.0.1. This is important because it ensures the testing is ethical and contained to our own system. For the tools, we use Nmap for port scanning, CURL to test HTTP, FTP to test FTP, and Telnet to test Telnet connectivity. Starting with Nmap scanning, the results show port 21 TCP and 23 TCP and 80 TCP as filter. In security testing terms, filter indicates that the scan probes are not getting normal response, which strongly suggests firewall filtering is active rather than the port simply being open. Next is FTP test. When we attempt an FTP connection, the behavior was immediate failure with a connection refuse style response. This matches our rule choice where we apply reject, because reject denies the connection and provide explicit feedback to the sender. Practically, this is useful when we want fast, clear denial instead of waiting for timeouts. Then we test HTTP using CRL. Here the connection resulted in a timeout, which demonstrates the effect of drop. The firewall silently discards packet without replying. This is a stealthier behavior because it gives less information back to scanner or attacker. Finally, for the telnet test, we again observe a silent block with a timeout. This is also consistent with drop, where the goal is to reduce visibility and make the block service harder to block. So overall, our results are consistent and meaningful. Nmap show filter for all targeted port. FTP show reject equal to immediate explicit denial, while HTTP and telnet show drop equal to silent timeout, proving our firewall rules are functioning as intended.
Okay, so for the entrepreneurial security proposal, for the first one is problem identification. So number one is home users. So many home users lacks awareness of network security and often rely on default system settings, which may expose unnecessary services to potential attacks. And the second one is small businesses, which is limited cybersecurity budgets and minimal IT staff make small business highly vulnerable to network breaches. And for the startups, fast-paced development and public-facing infrastructure often result in security being deprioritized, leaving critical services exposed. So for the second one is propose secure system solution. The first one is default deny policy, which is block all traffic except for essential services, reducing attack surface. And for selective rules, configure drop or for silent blocking, for example stealth protection, and reject for explicit denial where usability is critical. For the persistence, use Iptables, persistent and net filter persistent packages to ensure firewalls rules remain active after system reboots. And it is cost effective, which is open source solution with no licensing or additional hardware costs, suitable for home users, SMEs, and startups. Ease of management, minimum technical knowledge required for rule configuration, making it accessible to non-experts. For business and security value justification, the number one is enhanced security, which the firewall actively blocks insecure services for HTTP, FTP, telnet, and preventing unauthorized access. It also can reduce attack surface, which by only allowing necessary traffic, the system is less vulnerable to cyber threats. And then it can operational cost savings, which open source lightweight solution eliminates licensing fees and uses minimal system resources. And it also can improve reliability and trust, which effective security measures enhance system stability and user confidence, which is crucial for small businesses and startups. The last one is scalability potential. So the solution can be extended to multiple systems or integrated into enterprise and cloud environments, supporting business growth while maintaining strong security. So in conclusion, we successfully implemented and tested a host-based firewall using Iptables on Kali Linux, and it effectively blocks insecure services. So the effectiveness of Iptables, which the firewall actions such as drop and reject work as expected, showing that Iptables is a reliable tool for securing Linux system. Reflection on real-world applicability, Iptables provides strong security without extra costs, making it suitable for home users, small businesses, and startups. Its flexibility and open source nature allow it to be adapted for various real-world scenarios.